Yeah.
Good. So I just want to,
But we do want to record in case we have anybody who missed it and really wanted to watch it as well. So most of you know, a couple weeks ago, we did a presentation, our first vacation in space, with my sister, Nujood Moranci, and she talked us through the Artemis mission, which will be the next mission taking Americans and or astronauts to the moon. They'll be the next people to land on the moon, which I believe is scheduled to happen in 2024. And that was very exciting. If you didn't catch that one, we will be happy. I could be happy to send the link out to the communities again, and you can watch that as well. But today we have just a couple housekeeping items, and then I'll actually introduce our fabulous speaker. So housekeeping, please stay on mute unless you have a question. You can feel free to raise your hand digitally or as we get towards the end, any questions that you may have, please put them or ask a community team member there to put them in the chat, and I will be helping Dr. Evans with the questions and making sure that they get answered as we go through. So thank you everyone for attending today. A special shout out to Dr. Evans's father is actually joining us from Buffalo, New York today. So welcome, Mr. Evans, and we're glad to have you with us as well. I also see Regent Court Senior Living, or Regent Court has popped on as well. Hi, Regent Court. Thank you everybody for being on. And without further ado, I do want to introduce our speaker today. Dr. Cynthia Evans is the lead exploration scientist for the Astromaterials Research and Exploration Science ARES division within the Exploration, Integration, and Science Directorate at the Johnson Space Center. Trained as a geologist and an oceanographer, Dr. Evans earned a PhD in Earth Sciences in 1983 from the Scripps Institute of Oceanography, University of California, San Diego, and a BS in Geology from the University of Rochester. Prior to coming to the Johnson Space Center in 1988, she taught geology at Colgate University and Columbia University's Lamont Doherty Earth Observatory. She has several positions at NASA. However, I do know she's going to tell us a little bit more about herself, so I think she can probably give us a better introduction than I can. So I'm going to let her take over. Once again, if you put your screen on speaker view, then you'll get to see Dr. Evans, and I'll let her take it away. Go ahead.
Okay, thank you so much for inviting me to speak, and it's really a delight to be here. And before we get started, I actually have two fun facts for today. The first fun fact goes back to the 20th century. On this day in 1911, Roald Amundsen, the first person to reach the South Pole, left on his expedition. He took his first steps over the Ross Sea ice shelf on his way to the South Pole. And just a couple months later, he actually reached the South Pole, the first person to do it, ahead of the expedition of Scott, which of course was a really tragic expedition. The second fun fact is, in the middle of this talk today, NASA's OSIRIS-REx mission to asteroid Bennu is going to make its first sampling attempt. It's been many, many years in coming. The mission was formulated about 10 years ago. It launched in 2016. So it's taken this long to get to the asteroid. And today it's going to try to do like a little pogo stick, bounce off the surface of the asteroid and collect some asteroid samples, which we will tie back to meteorites. So anyhow, I'm going to talk to you about collecting meteorites in Antarctica. And the first thing I'm going to do is show you a little video that was made from my last expedition, which was in 2015. So I'm going to share my screen. And I'm going to choose, I got to put my glasses on, and I'm going to share. And this is, okay. Can you see that?
Looking for meteorites is actually like finding little gifts from the universe. And these things are priceless because we're able to sample bodies in the solar system that we've never sampled before. Even though these aren't gold nuggets or diamonds, these materials represent bodies that we have never gone to. And so they are absolutely invaluable. My name is Nina Lanza, and I'm a staff scientist at Los Alamos National Laboratory, and I work on the ChemCam instrument on the Mars Science Laboratory rover. And I also had the opportunity to go to Antarctica with the Antarctic Search for Meteorites.
Nina's 9 to 5 is out of this world.
I'm kind of excited about this cliff here. My job is the best job in the world, I'm not gonna lie. So my day job, of course, is, shooting lasers from a spaceship on Mars. So that's awesome. That was my, dream come true. But I had this opportunity to help find meteorites, and I felt like I was following in some, the footsteps of some really big explorers like Shackleton and Scott and Amundsen, who actually was the first to get to the South Pole.
Every year, small groups of scientists venture out there on the most extreme of treasure hunts.
I know it's no surprise to anyone that it's cold, but it is really cold there, even in the summer. So we were there during Southern Hemisphere summer, so that's December and January, but it was actually 0 degrees Fahrenheit on average during the days. However, I did measure a temperature as low as -8 degrees Fahrenheit, which is getting a little more brisk.
That's about, minus 22 Celsius. Then there's the wind chill.
I think the highest wind speed that I measured was about 62 miles an hour. If you expose your skin to that kind of temperature and wind speeds, it feels like things are cutting your face. It feels like something is touching you and cutting you. It's really harsh. Of course, we try to cover all of our skin, but in order to speak to each other, you have to pull down your balaclava and then you expose yourself just a little bit to the environment.
It begs the question, why go all that way looking for space rocks when you could do it in the warmth and comfort of, say, New Mexico?
There's not more meteorites falling there than anywhere else on the Earth, but 71% of the Earth's surface is covered by an ocean. So most of the meteorites fall right into that. And so that's harder for us to recover, of course. And then once they get in the water, they basically dissolve. And so we lose those materials. Antarctica is special because it is covered by glaciers. So meteorites will fall in to snow or ice and then become embedded. When there's very high winds, you can actually scour away the ice and all the rocks become exposed at the surface. So we can just walk around and pick them up. They actually are really pristine. They're very similar to the state they were in when they were in space. So this is an incredible resource for us. I think it's about maybe 80% of the world's meteoritic materials that are found per year come from the ANSMET project. So it's an incredible way for us to sample throughout the solar system without leaving home. A typical day, meteorite hunting usually starts with preparing your food and water for the day. It takes about 8 to 9 minutes to actually put on all your clothes. And you don't want to underdress because you can't come back and get more clothes.
Waterproof, down insulated snow pants.
Fantastic. Look, and it's the color of ice.
Liner pair underneath.
Yeah.
We're getting there.
We get into a formation. So we kind of line up. And there are 2 people on the edges who are in charge of putting flags down.
The flags are used as place markers until GPS measurements are taken.
And then we kind of are in a semicircle, and we're driving very, very slowly. We're talking like 2 miles an hour, and we are just scanning back and forth. When you see a rock and you think it might be a meteorite, you make the international symbol for come here. And then your teammates will all come over and we'll take a look at it. And we will decide whether or not this is a meteorite or a meteor wrong. It happens. And if we decide it's something that we want to sample, then we have a sampling kit that we pull out.
6 by 4 by 3.
We never touch the meteorites directly. We really want to lessen the chance that there's any contamination from us because people use these meteorites to look at organic materials. And of course, we're covered in organic materials. We don't want to add those in.
Nina and her teammates spend about 9 hours a day doing this.
So we bring all of our food with us. Of course, there's nothing on the continent for us to eat, but we don't bring water because we are surrounded by water. The way that we get our water is by using an ice pick and chipping ice out of these glaciers and then melting it to drink. And it's the most delicious water I have ever tasted. There's nothing like, a 12,000-year-old ice cube. It's incredibly pure. I think I've been spoiled.
The expedition lasted 5 weeks, but the treasures they found are timeless.
We found a total of 569 rocks. most of which we think are meteorites. We won't know that until we get these into the laboratory, even though we find all these meteorites as a team. So we never talk about who actually found which, although of course people may be keeping tabs. I may have done that. All I'm going to say is that I found a good 10% of the meteorites.
Yep, not too shabby for a first-time space rock hunter in the harshest place on Earth.
I don't know if I could ever say that I was as swashbuckling as Indiana Jones, but certainly Antarctica was a great adventure for me and everyone else there. You've got to withstand a lot of physical challenges and at the same time do the science that you were sent to do. The thing that I was surprised about was how the isolation affected me. No matter how great your teammates are, they're still not like your closest friends and family. You know, you don't have your email, you have nothing but the wind and the sun and the cold and each other. And I felt like, you know, that kind of isolation is something I never experienced.
That said, Nina was crystal clear about one thing.
I would love to go back to Antarctica for another expedition.
Okay, I'm going to, let's see here and try to share my other things. So that was my friend and colleague Nina, and I went to Antarctica with her in 2015 and 2016. And now what I'm going to do is I'm going to unpack that a little bit for you. So talk a little bit more about the who, what, where, when, how, and why. So as Amira had mentioned, a little bit about me. I am a geologist. I was trained at a school of oceanography. I've been on a bunch of oceanographic expeditions. I consider myself a field geologist. I've been on several field campaigns. And I spent 30 years at NASA, and I've worked on a variety of projects. I've done Earth observations from the shuttle and the Mir space station and the International Space Station. I led the curation office. I led the Astromaterials Research and Exploration Science Division. And right now I'm helping to formulate some requirements and plans for future science operations when we go back to the moon, and also help train the astronauts for going back to the moon. So that's super fun, super cool. And I've been lucky enough, extraordinarily lucky, to be on 2 Antarctic expeditions to collect meteorites. And so just the pictures here, there's a picture of me in the field, a picture of me in Antarctica, a picture of me in the curation labs, and a picture of me with some astronauts doing some field training. So next. But the bigger who, I'm the little who, the bigger who is the U.S. Antarctic Search for Meteorite Program, which we call ANSMET. And you can see our logo, which is a penguin catching a rock from the sky. And the great thing about ANSMET is that it's a collaboration across 3 federal agencies, NASA and the National Science Foundation and the Smithsonian, as well as the whole planetary science community across the world, not just the United States, but across the world. And so I think it's pretty unique in that regard, that it's across all these different agencies, and it really is meant to benefit everybody. It's like the best of what government does. It's a US-led field-based planetary science project, and the purpose is to recover meteorites. And the thing that's great about meteorites is that they're ground truth for the study of all kinds of things from the early solar system, for asteroids, but we also have meteorites from Mars and the moon. And these meteorites that we collect in Antarctica can be requested by any planetary scientist from around the world, and it doesn't cost anything to request them. And if somebody's request is reviewed and deemed acceptable, we just ship them out to them. It doesn't cost anything. The program itself began in 1976, and originally it was funded by the National Science Foundation. One of the founders of the program, Bill Cassidy, just passed away this summer, but he had this vision of modeling it after the Apollo program, making sure that the samples themselves could be available to the whole community and not just buried in some academician's private collection. Today, it's funded by NASA's Near Earth Object Program. And to date, over the more than 40 years of ANSMET, we've recovered more than 24,000 meteorites, which is about 50% of all the meteorites worldwide. So it's really a productive program, and it's for science and education. There are other nations that have Antarctic science teams to collect meteorites, the Japanese, the Chinese, the South Koreans, many European countries. They don't go every year. The United States-led program is by far away the largest. And any season, given season, we might find 100 meteorites. We might find more than 1,000 meteorites. 500, 600 is average, but it depends on the size of the field party, where you go, what the weather is, how long you're out. So Nina had mentioned that in 2015, 2016, we collected 500, almost 570 samples. This past year, we collected 346, I believe, samples. And it's just dependent on a whole bunch of other things, which I'm going to talk about. So my 2015 team, you saw that nice video, was a team of 8. Similarly, the team that I went on in 2019-20, December and January, this past December of January, was also a field team of 8. It was led by the principal investigators, Dr. Ralph Harvey, who's at Case Western University, and Dr. Jim Carner, who's at University of Utah. Neither of them were actually out in the field with us, but they are the ones that put together the program. Generally, one or the other of them actually does come out into the field, but this past year they didn't. And the purpose is to collect pristine meteorites from the deep field, and they're going to curate them and make them available for study. And we went out this year to the Davis Ward Nunataks. And nunataks are like mountains that are buried in the glaciers. So there's the little tiny tips of the mountains that are peeking up over the ice. It was about 85.5 degrees south. So we were just shy of 300 miles from the South Pole. So it was really cold. It was colder than my first deployment, which was to the Miller Range, which really was pretty balmy. Both of them were beautiful, beautiful places. And we were out for 2 months. We were deployed for 2 months. We were out in the field for a little over 4 weeks. And I was sponsored through NASA and my affiliation with the ESSA Materials Research and Exploration Science and the Curation Office at NASA. And just in case I forget to mention it, at the Johnson Space Center, we curate all of NASA's extraterrestrial samples. So the Apollo samples from the moon, the meteorites, the samples that are being collected this afternoon. We have cosmic dust that are collected by high altitude aircraft. We've got samples from a comet that were collected on the Stardust mission. So all the extraterrestrial samples are curated at the Johnson Space Center. Another fun fact. So here's our team. So a team picture with our little camp in the background. In the upper, like sort of a top row, there's me with the white hat, and my tent mate, Emily Dunham, in the olive green cap. Emily is a postdoc at UCLA. She studies meteorites. Down below me is Alex Gerst, Dr. Alex Gerst. Alex is a geophysicist, but he's also an astronaut from the European Space Agency, and he's been on the space station twice for a cumulative time of about a year. To the right of Alex is Dr. Mark Caffey. He is a geophysicist from Purdue University. Down below Mark, the lower right, is my teammate Lauren Angadi. She just got her master's degree in planetary science from Case Western, and today she works for the EPA. To the left of Lauren is Nicole Lunning. Nicole, Dr. Lunning also works at the Curation Office at the Johnson Space Center. We just hired her. And then the two guys over in the bottom on the left-hand side, the one on the far left with the mustache, the white mustache with snotsicles, because it's so cold, is Johnny Scott. Johnny is our mountaineer. This was his 39th deployment to Antarctica with ANSMET. And then Brian Ruggie, who's our other mountaineer, and he's been out 6 or 7 times. So it's a cast of characters. You get to know them really well because you're out in the middle of nowhere in pretty tight quarters, and it's great. So what are meteorites? They are rocks that fall from the sky onto the earth. And most of them come from the main asteroid belt. So we have a little graphic of the solar system in the upper right. The sun's in the middle, then there's Mercury and Venus and Earth and Mars and Jupiter. But between Mars and Jupiter is a pile of rubble, and that's the main asteroid belt. And they're chunks of rocks from small planetary bodies that were formed early in solar system history that didn't quite make it, that got smashed up. And most of those are very old, like 4.5 billion years old. too many keyboards here. So as extraterrestrial samples, we also call them astromaterials. So those are the two same things, a sample that came from not of the Earth, they're extraterrestrial or astromaterials. The meteorites are important because they are representative of some of the very earliest stages of solar system evolution, some of the early things to condense out of the solar nebula, parts of early planetoids. And they provide evidence for the primordial materials and the early processes in the solar system. So the abundance and the composition of materials, including organics, including volatiles like water, and they give evidence for early planetary differentiation, when all the stuff stuck together, like the Earth is a differentiated planet. It has layers. There's a core, there's a mantle, there's a crust, and it's not the only body that formed into layers. And also the way things got altered over time. And we do have samples from Mars, and we do have samples from the moon. In fact, the only samples that we have from Mars come to us as meteorites. We have never been able to go to Mars yet and pick up a rock and bring it home, although we're trying to do that now. And we also have samples from the moon, meteorites that were blasted off the lunar surface that landed on the Earth, that were not collected by the Apollo astronauts. Why Antarctica? So this is a picture of our field area, and it's really, really beautiful. So this is, let me see if I can use my cursor. I don't know if you can see my cursor. So this is the end of a glacier. We call it the Big Tongue. So you're going to hear about the Big Tongue, and you'll see a map of the Big Tongue. So this is called, this is called blue ice. And around it, the brown stuff, that is a moraine. So it's the rubble pile that was carried and pushed by the glacier itself. And the reason why we go to Antarctica is because it presents a wonderful geography advantage. The ice and the wind and the coldness and the dryness are all really important. So a map of Antarctica, the South Pole is right here in the middle. This blue arrow represents the flow of the ice. On the South Pole is covered by between 2,000 and 3,000 meters, 2 or 3 kilometers of ice, the ice sheets. And it's a mound, and it has a tendency to want to flow down. So it flows down from the center, which is at the pole, towards the coast, which is to the north. And it carries with it anything that happens to fall on it. So meteorites fall everywhere equally. They do fall in the United States. They fall in Oregon and California and Idaho and Buffalo, but we generally don't find them because there's water, and there are trees, and there are bushes. And in Antarctica, there's ice. And so the moving ice acts as something like a conveyor belt. It just moves everything, all the meteorites, thousands, tens of thousands, hundreds of thousands of years of meteorite falls from the towards the coast. And if the glacier itself gets rammed up against an obstacle, and in this case, the obstacle is the Trans-Antarctic Mountain Range, which is this gray area that I'm going. So if it rams up against mountains, like we see in this cartoon over here, the ice stops. And then the cold winds, the katabatic winds, they're density-driven winds, also flow northwards from the pole, and they just ablate the ice away. So you get the lower parts of the glaciers exposed, the blue ice. And this is where we find the meteorites, the slow-moving or not moving at all ice that's been ablated away. And Antarctica is a perfect place for it. And we go to several different locations along the Trans-Antarctic Mountains. And so just also for geography purposes, so this is the Antarctic Peninsula. And so the South America is off in this direction. Ross Island, where McMurdo Station, the prime US Antarctic base, is right over here, and this direction towards New Zealand and Australia. Okay, we're gonna go forward. So where did we go? We talked about the Davis-Ward Noon attacks, and there's my cursor, which is this blue area here. These squares over on the left-hand side along the Trans-Antarctic Mountains represent maps for over 50 sites along the Trans-Antarctic Mountains where ANSMET's been. And if we look at the blue area, map number 3 is represented on the right-hand side, and the blue circle is where we went. So it's right at the southern end of the Beardsmore Glacier. And Beardsmore Glacier is notable because that's the glacier that Admiral Scott took to go from the Ross Sea towards the pole for his journey. So it's way out there. We're kind of the last little rocky outcrops before the South Pole. And another picture of where we were. Let's see here. There we go. So if we look at here, this is a picture of the Earth taken from Apollo 17 by the Apollo astronauts. So the South Pole is down here. The red star is about where our field location is. And again, you can see really how far we are. And, you know, the South Pole is not that far away, only like 200 or 300 miles. That's the closest civilization. Oops, there we go. And that's the picture, that's a satellite picture of where we, of the Big Tongue. Okay, so getting there, it's all about logistics. So this is part of the how. So first we have to get to McMurdo Station, then we have to collect our field gear, then we have to do a whole bunch of training on environmental regulations. We have to get our equipment, get trained on our equipment. We have to have learn about team and personal safety. We have to package all of our stuff together to get into the air cargo stream from McMurdo, which is kind of like a logging camp. And it's where you do all your base assembly before you go out into the deep field. For a 6-week deployment, it's about 1,500 pounds of stuff that we have to schlep all the way across the continent to our field location. The National Science Foundation and the United States Antarctic Program help coordinate all that. And sometimes we have to do other field preparations, like a couple people had to deploy early to make a runway out on the ice so that bigger aircraft, a DC-3 or a Bastler aircraft, could actually get out there. So, but before we get to McMurdo, we go through New Zealand. And so this is our first stop at the New Zealand airport for the clothing distribution center, where we get all the extreme cold weather gear, the big red jackets that are called Big Reds. There's some of our team, including me, in front of the terminal right after we'd arrived, got all of our stuff, and we were really excited because the plan is then the next day to get on an aircraft to go down to Antarctica, and the aircraft are C-130 cargo planes. Which we see over on the right-hand side. But it didn't quite work out that way because there was some weather, and then it took us actually 10 days of waiting. And every single day we'd get up, we'd be ready to go to the airport to get on the plane. And then we'd get a little piece of paper that would say, well, you're delayed. It's a no-fly day tomorrow, and it's a no-fly day tomorrow, and it's a no-fly day tomorrow. But each time you have to get up at like 6:30 or 5:30 or 4:30 or 3:30 in the morning, get everything together, schlep all your gear down to get transported to the airport, and boom, boom, boom. And finally, on December the 13th, our lucky day, we were able to get out of Christchurch, New Zealand, which is a wonderful place to be stuck, by the way, and get on our airplane and get down to Antarctica. So we were delayed by 10 days, but we got to McMurdo, and McMurdo is also a really wonderful place. It's like a logging camp. There are, see if I can get my cursor. There's a cafeteria, there are dormitories. It's a really, really nice science building. All different kinds of science teams do science there. Marine scientists and upper atmospheric scientists and glacial scientists. And some of them get deployed to the field. Some of them get deployed. Some of them do their work around the McMurdo. And there's lots of big equipment with huge wheels. It's a really interesting place to be. So while we're there, we have to get all of our gear. This is Lauren and some of the field gear, our sleep kits, some of the kitchen gear. That's just like one person's worth of gear. Get all of our food. This is Alex, and just a small portion of the food that we had to collect for 6 weeks out into the field. And it's a daunting task to go shopping for 6 weeks for 8 people at the little food distribution center. Then we have to pull it all together, and under the best of circumstances, we and some of our gear get deployed out into the field relatively quickly. We also do a little shakedown cruise. We take our gear a couple miles out onto the ice shelf, and we practice camping to make sure that we know how everything works. But then we really have to wait for all the stars to align. And that includes weather across the continent, the science priorities, because they get reshuffled, the aircraft availability, the aircraft maintenance. And again, it took us a couple of weeks once we got to McMurdo, to get out into the field, because there were just so many things that had to fall into place. So while we were in McMurdo, we got a chance to explore a little bit. So we got to know some of the natives. This is a Weddell seal. In the summertime, in December and January, the Ross ice shelf begins to crack. and the seals just pop up along these cracks. And so there are dozens of seals in this picture here, and they're huge. They probably weigh a couple tons, and they just kind of lie around on the ice all day long. We also got a chance to see some penguins, Adelie penguins, and in fact, this video was taken right when we came back. There was a whole bunch of them that just decided to march through town. We can't go anywhere near them. If they come near you, that's okay. But it was just the funniest thing to watch all these Adelies come just tearing through town. Oops, and there we go. And some of the other natives are the people that work in McMurdo. This year, the whole of the Antarctic continent is shut down pretty much because of COVID. And it's really tragic because there's so much really important science that should be getting done, understanding climate change, understanding how the ice is melting. But we have to put that off for a year. But there's still a skeletal crew in McMurdo this year to keep all the logistics and the facilities going. But usually in the summertime, there's about 1,000 people in McMurdo. Right now, there's maybe 400. But they work really, really hard. They work 6 or 7 days a week. And then sometimes they have a day off. So we were there for Christmas. We had a wonderful Christmas dinner. The cooks are fabulous. But then on Christmas Day, there's an all-afternoon softball tournament in McMurdo. And the rules are a little bit different. You have like two outs per inning and maybe 5 innings per game. And let's see if I can find my cursor. Costumes are encouraged. There may be some adult beverages involved, but the team itself is really, really tight, and it's great to get to know all the people that make your science happen. Okay, so now we get out to the field. We finally got out in the field just before New Year's. This on the right-hand side is a satellite image of the Big Tongue, our glacier where we're going to be collecting samples. And this is a view of it from the aircraft. And our little camp is in this box here, and you can't see it very well. So there you go. There's our little camp set nestled in amongst these nunataks, these little tops of mountains that are buried in the ice. And you can see the blue ice. So the area that we went, the Davis Ward area, had been visited 6 times before by Ansmet Field Seasons. And on the right-hand side, the map of the Big Tongue, all these little dots represent an area where a meteorite was found. So you can see a lot of meteorites have already been found. And our goal was to finish the area off, to finish doing systematic searches of the entire area, including the area way up at the top. We set up camp and then we commenced searching. And there is a couple of different methods of searching. Nina talked about them a little bit. One of them is the systematic searches on the blue ice, where we get on our snowmobiles and we basically do like a search and rescue search. So if we look at the map of our glacier, the area that doesn't have any dots is the area that we were responsible for kind of covering. And we would set up in an array, and we would just go in one direction and look for rocks on the glaciers. And then if we didn't find any, we'd turn back around and we would sweep back and forth and back and forth. And these are pictures of what it looked like. And if you happen to find a rock, we'd stop, do the international sign for I found a meteorite, and then we would all get together and collect it in a uncontaminated, pristine way. Sometimes, especially at the margins of the glacier, there are a lot of rocks, and we actually had to look at all of the rocks that you see over here on the right-hand side. So this is a rock that my colleague Mark Caffey and I found together. We were on either side of it on our snowmobiles, and we both found it at the same time. So we had to have our picture taken with it. But it's a really beautiful picture of a meteorite to show you what they look like. So it looks a little bit like a truffle, right? Like it's got like chocolate on the outside, maybe some creamy nougat in the middle. But this chocolate on the outside is really the fusion crust. So when a meteorite falls through the atmosphere, it gets really, really hot, and the outside melts and it forms a fusion crust. And then it preserves the inside material. On the inside material, there's some of these early building blocks from the solar system, little chondrules, little round chondrules, and some other things as well. So this is an ordinary chondrite. The other way of searching is when we get to the margins of the glaciers where the moraines are, you have to, there's a lot of rocks. And so we just do foot searches, or in my case, I would usually get on my hands and knees and do crawls trying to find meteorites in these rocks. And that's a really daunting and arduous task. But some areas that you would just find several, or sometimes tens, or sometimes dozens of meteorites. And then we would, again, we'd mark them with red flags and we would collect them. And in some cases, like these two areas, these windrows and these moraines where there are really high density concentrations of moraines of meteorites, it's just kind of mind-boggling that you would find so many meteorites in such a small area. Every single one of those little flags represents some place where a meteorite that we found and we identified and we collected. So that's how you get hundreds of meteorites. And you can see the whole team is operating together. So these two pictures have meteorites in them. And sometimes we do presentations like this and we say, find the meteorite. Where do you think it is? It's hard to do that. But I'm going to try to, so you can see all of these rocks, they're all about the same size, but some of them are different. Like this one in the middle, it's meteorite and it's more round and it's shiny. That's that fusion crust. And so once your eye gets tuned into that, you can actually pick them out pretty well. On the picture off to the right, and I actually can't see it because everybody's picture's over it, but there's like a little, I think right around in here, there's another, it's rounded, it's a little bit blacker. That might mean it has organic material in it. So maybe it's a carbonaceous chondrite. But that's what we look for. So that's what we do all day long, every single day. A little bit about camp life. Our camps are simple. We live in Scott tents. They're not very different from the kinds of tents that were used by the explorers. Let's see, what time am I? So a picture of what our camp looked like from the top of the Nunatak. And this is our camp from the ground. And that contrail, that contrail is a plane that went from McMurdo Base to the South Pole. And so the South Pole is the end of the contrail, and the contrails will last for hours, but it was really nice to sometimes have a plane going overhead, and then where it would end or where it would begin, you know exactly where the South Pole was. So it was not that far away. There was nothing between us and the South Pole. The tents themselves are remarkable camping experiences. Each set of two people, and my tent mate Emily is down in the lower left-hand picture there. 2 people to a tent. They're like 9 by 9 by 9. We have Coleman stoves for cooking, and when we're cooking and when we're just up and about and reading inside the tents, we have those stoves going, so that it's pretty warm inside. It gets pretty toasty. The bottom of the tent might be minus 30 or minus 40 degrees. The top of the tent might be 100 degrees. So we use the top of the tent to warm things up. We thaw out our food. All of our food is left outside in the refrigerator that happens to be the world, or the freezer that happens to be the world. We hang our boots up to dry them out. We defrost our food. Sometimes we get together. We have one tent that was the little laboratory, the poo tent. Then we have another tent that was the science tent. So we get all together. Every single night we would get together in the science tent, and we would talk about the day and talk about the next day. And we would read the diaries of the explorers. If it was December 29th, we'd read what Amundsen was doing on December 29th. Who he had already turned around and was heading back. We'd read what Scott was doing. We'd hear about their experiences. Sometimes we would party. But it was pretty tight to have 8 people in a tent like that. We kept a schedule that was pretty strict. We'd wake up every day at 7 a.m. and we'd have a weather assessment. It would usually take us a full 2 hours to get ready, including, for me, it would take at least 30 minutes, sometimes 40 minutes to get dressed, to get all the layers on. We'd have really long days out in the field, at least 8 or 9 hours out in the cold. It would be between -5, -10 degrees every morning when we got up. If the wind picked up, it felt really cold, and then we'd get together every night after dinner. So the 2 pictures on the left were taken at midnight on on December 31st. So at the midnight sun at New Year's, actually the very first minute of the new year, we are celebrating. If we, for some reason, couldn't go out in the field and it was nice enough, we'd often do things outside. Like this is a cribbage game that we sort of set up on a nice sunny afternoon. And then we also have to just take care of daily life. So this is a picture of me getting water.
Go.
Chip and ice. It was one of my favorite activities. And the goal is to get as big as a chip of ice, and we'd have to fill a bucket because the bigger the chips, the more water and the less time you have to go chipping. So that's what we would do.
Go.
Yep. All right, so end of the season. Our goal was to finish searching this whole area, and we didn't quite get there for a variety of reasons. We had some bad weather where we couldn't go out into the field. We had some unexpected discoveries that took us longer. But in the end, we collected 346 specimens, and this is a picture of all of our meteorites packed up, ready to be shipped to McMurdo in a Pelican case. And actually, this thing gets bundled up and locked up, and we don't open it until we get it back to the Johnson Space Center, and it's kept frozen the whole way. So there's another field team is going to have to go back to the Davis Ward to finish it up. But the astounding thing is, over 7 seasons now, we were the 7th season, more than 3,300 meteorites were found in this area. So it's a tremendously fruitful area for finding rocks from the early solar system, rocks that fall from the sky. It's just a truly phenomenal thing to participate in. So going forward, what happens next? The samples come back to the Johnson Space Center. Not only do our curation team prepare and ship all the collection materials that include the sterile collection hardware, the sample bags, the tape, the shipping containers, but they also do all the initial processing of the meteorite after the season ends. And it usually takes a couple of years, and this year it's going to take longer because they haven't been able to get into the laboratory because of COVID, to take a season's worth, several hundred meteorites, and process them, give them a field name, characterize them, and then announce them for availability to researchers. Nobody gets dibs on a meteorite. They get announced to the community at once, and then the entire community can request samples. We maintain a database that the community can use, and then we've got staff that have participated in ANSMET and know about the meteorites, and they can answer questions about NASA missions and sample return and curation and contamination control and human exploration. So, and this is kind of like a little map of the life of a meteorite, like what we do to it. And then here's the samples in the field when we received them in March at the Johnson Space Center in a refrigerated FedEx truck. We put them into the laboratory immediately into a freezer, and then they get processed under dry nitrogen one by one. Finally, a little bit about the benefits. So, it's a low-cost sample return mission. A mission to go to the moon or to go to Mars or to go to the asteroid Bennu, like the OSIRIS-REx mission today, costs billions of dollars. But this is a way of getting a lot of planetary material in a really low-cost way to address all kinds of questions about what went on in the early solar system. These samples also provide information for other missions, like the OSIRIS-REx mission that's happening today, the Hayabusa 2 mission that's a Japanese mission that sampled an asteroid about, last November, I believe. And it will also inform our missions to Mars. And it's an analog mission for understanding the scientific operations for planetary scientists, for engineers, for astronauts. So it's surface science operations. It's a relevant environment for remote operations. You're really remote. It's really hazardous. But we have documented science returns, and we learned that it's all about the logistics. We have to respond to the unexpected, like flight delays, like weather, like breakdowns, like scheduling, like priority shuttles. And all these are really important lessons for conducting exploration and conducting science operations. And finally, it's an international thing too. Not only is there cooperation across 3 federal agencies, but we have international partners, and that's a great model for future lunar exploration. Provides field training for planetary scientists and future NASA leaders. I was a geologist. I spent a lot of time in the field. Many planetary scientists end up working in the laboratory, and they don't have a lot of field experience. And so this program brings in a lot of young planetary scientists, and it provides a mechanism to reinforce expeditionary practices and mentorship for early career planetary scientists. And that was kind of my role, is to be a senior scientist with several of my early career colleagues. And even for field geologists like me, there's stuff that you've never seen before. And for me, the lesson is you can look at someplace from a satellite, you can think you understand it, but it's until you get on the field and you see things that you realize it's going to be different. It's going to be a unique geology, a unique shape. It'll be different from anything else. And that the relevance is that when we go back to the moon, even though we will have done lots and lots of studies from satellites, we won't know what we see until we get there. So the outcrop scale geology is going to have surprises, and it's going to require critical observations, and it's going to require a well-trained crew and well-trained support teams. We learn to manage our expectations. We learn the value of flexible plans. All field campaigns end up replanning. We call it fluxecution. So there's always unexpected field results. Like we had new concentrations that we had to stop and survey. So that's part of the excitement of exploration. And finally, we do have outreach to the whole public. We maintained a daily blog. It's on the ANSMET website if you were to Google ANSMET, and talk about the relevance of our work, provide some snapshots of the many facets of daily life, some of the logistical challenges, and just the general excitement that the team experienced. So that's all that I have. This little link in here is actually another BBC sort of overview, but I know that it's hard to play links over Zoom. So and I've included some of the web pages that we have: the ANSMET web page, the curation web page here at the Johnson Space Center. You can follow us at NASA Astromaterials on Twitter. We have a Facebook and an Instagram pages as well. And I think I'm going to stop there and see if there's any questions. But thank you so much for having me talk. As you can see, I'm really excited about being able to collect rocks from space, and it's excited to be able to share that with you. And I'll stop sharing. And there we go.
Thank you, Cindy, Dr. Evans. I do want to throw out here that please, in the chat, if you haven't already, please put in the city and state where you're from, just so we can kind of collect and make sure that we get everybody that's attended today. We really do want to know where you're from or where your group is watching from, so that I can also share that with Dr. Evans and we can see how cool it is to connect everybody across the country. In this sense, it sounds like Dr. Evans was connecting everybody across the world, including Antarctica. So thank you so much. That was really informative and really exciting. So thank you. And so I do want to open it up as well for questions. I know last time it was easiest maybe for anybody to throw it, type into the chat box any questions that you may have thought of or are dying to ask. But also, if you'd like to ask it yourself, I'd also welcome you to unmute yourself, and you can ask the questions of Dr. Evans yourself. So I know thank you everyone for putting, I do have a question from Mr. Royer, I think in Payson, Arizona. Is NASA doing any research on the thorium breeder element 233 or 232? Sorry.
I'm not sure I can fully answer that question, but one of the things, and I think there might be two kinds of questions here, but in terms of studying these samples, so if there's information about like perhaps nuclear power, I'm not the person. NASA is working on nuclear power for spacecraft and for operations, but I'm not the person to answer that. But if you want to talk about the composition, we have the whole periodic chart in front of us, and trying to understand the evolution of the solar system. Every single element on the solar system is up for grabs for study, including uranium and uranium thorium and uranium lead systems, to understand both the abundances and the dates of materials, So one of our big challenges is that's why we have to keep things as uncontaminated as possible, because the abundances of some of these elements is so low that going into the laboratory with a gold ring, and gold has lead in it, and lead can potentially contaminate your samples. It volatilizes really easily. So we have to really minimize the amount of materials that we have in the curation laboratories, and the potential contamination that we have even while collecting the samples, so that we don't accidentally add terrestrial abundances of elements to the samples that we're trying to parse out the cosmic abundances of. I don't know whether that answered the question or not, and I apologize.
Well, I do have another question though, too.
Okay.
Actually, it looks like it comes from Roseburg, Oregon. If meteorites fall each year, wouldn't you need to revisit areas again?
Absolutely, yes. And the other thing is, but the meteorites that we collect, say on the Big Tongue, that glacier, they've accumulated over tens or hundreds of thousands of years, so a really long time. And so 1 year's worth of flux, and also they were carried by the conveyor belt of the moving glacier. But the other thing that happens is that some areas are covered by snow, and 1 year, and then the next year the winds have come and scoured away that snow, and then there's new meteorites to find. And so we know that even though we try to do we have systematic surveys and we're trying to finish an area, we're never finished with an area, because meteorites might fall, and they might be covered, or they might be uncovered, or we might have just passed them over, because sometimes that happens too.
Nice, thank you. We do have some more questions coming in. Thanks, everybody. Is the Big Tongue what your crew calls it, or is that an official name?
That is not an official name. That's just our field name for that glacier, because it looks like a big tongue. And you can see that, like on some of those maps, we had other names. The beach was part of their moraine, where it was kind of like a pebbly beach. The trough, which is an area where the glaciers themselves are not flat. There's a lot of ups and downs on them. And there's an area where there's a big trough, and it was called the trough. So no, those were just like our field names for the geographic features that we had in the field. The mountains themselves had real names. There was Mount Ward, there is the Beardsmore Glacier, but our little Big Tongue is just our little Big Tongue.
We do. So how do you determine where you go next?
Okay, so there's the principal investigators, Ralph and Jim, and Johnny and Brian, the Mountaineers. They have a multi-year plan, and the whole planning process takes place like over a couple of years anyhow. So they always have an evergreen plan, because sometimes there's an area they might want to go to, but the logistics in Antarctica won't allow that because of other science that's happening there. It all has to kind of weave together. So the past few years, there's been a focus on the Davis Ward to try to wrap up that area. A few years ago, I went to the Miller Range, and again, it was an area that had been searched by several teams but hadn't been completely finished. But then there are other areas that they know there's concentrations in, and that they want to get to in future years. And so they have like a primary plan, and then they have lots of backup plans. They have to put in the plans. They have to provide them to the National Science Foundation kind of by this time of year. Well, actually, no, it's by, I'm thinking the time has gone, has escaped us, but by early, as soon as we get back, you have to file the plans for the next year. So like in a couple months time, they'll plan for the 21-22 season, and hope and cross fingers that they'll be able to get down to Antarctica this year, because they can't get down. They should be leaving in about a month's time, and they won't be able to get down there this year.
Nice. Thank you. You said you need to test to make sure they are really meteorites. Is that done on site before they're shipped in the containers?
No, when we package them up, we seal them up, and then we don't touch them again. So that happens back in our laboratory at the Johnson Space Center, when each sample gets unwrapped and it we assign it a real name from the field name and dry it out under nitrogen so that you don't have water oxidizing the sample, and then chip off a little piece and make a little thin section of it and do like a first level characterization of it. Sometimes the initial characterization is wrong, but it's enough to let the community know, we think we got a sample of a carbonaceous chondrite. We think we got a sample of the moon. We think we got a sample of Mars. Think we got a sample of whatever the kind of meteorite it might be.
Nice, thank you. I don't see any other questions in the chat at the moment. However, I do have a couple of questions that I think, are interesting to know as well, in that, you have a background in geology and oceanography. Is there a collection of backgrounds and degrees that these scientists come from in order to be put on these expeditions? How do you get on the expedition?
So there's people come and Ralph and Jim, the PIs, with Johnny's inputs, they cast a really wide net, and that's one of the wonderful things about the program is that they bring mostly planetary scientists, but not all planetary scientists. And so it's like Alex, is not the only astronaut that's gone, but they've had other astronauts. Alex happens to be an astronaut that was a geophysicist, but they've had other astronauts that come from different kinds of engineering backgrounds. For example, the year before I went, there was a colleague at the Johnson Space Center who was an engineer, and so the way you get to participate is you write a snail mail letter, not over the email, and you send it in to Ralph and Jim because they want to make sure that you're serious about it. And they get hundreds of letters requesting participation in the field season every year. They have to go through and kind of vet the ones that they are serious. Most of us, before the first time we went, put in a letter every year for like 5 or 6 years to document, why you want to go. You have to be able to say, I want to go because, in my case, I wanted to go because, I sit on the boundary between planetary science and human exploration, and also being, associated with the curation office. I wanted to know, from cradle to grave, how the samples get collected and, their whole trajectory. Other people have other reasons, and like many of the colleagues that go are in fact meteoriticists, planetary scientists. They study these things for their day job.
Wow. It sounds like, well, and it's kind of nice to know too that we still use good old fashioned writing a letter for something as high tech as looking for meteorites. Although it sounded like you had employed some very low tech techniques for finding those meteorites as well. So that was something certainly I didn't know. So I haven't seen any other, well, we have 2 minutes, but haven't seen any other questions come through, although several comments have come in that you've now inspired several people who want to go chip ice and look for meteorites in Antarctica. I don't blame them. I'm actually kind of excited. I would be very excited to do that myself. But on behalf of everybody from our company and beyond, it looks like I saw in the chat, we had some more people from New York also joining us today all around the country. And so Dr. Cindy Evans, thank you so much for your time today. And this was very, very educational, very beneficial. And I'm seeing lots of notifications that people really enjoyed it. So thank you.
It's absolutely my pleasure. And so thanks to everybody for joining. And I hope that you got something out of it. And I know you're going to have an exciting talk in a couple of weeks. So I'm going to join in.
Thank you. Actually, you just reminded me before everybody gets off, please join us. Yes, we do have our next session is on November 10th. And that's at the same time, 1 p.m. Pacific time. But November 10th, we have Dr. Eileen Stansberry joining us, who will be speaking about NASA's crown jewels, moon rocks, stardust, and more. And so join us for Dr. Eileen Stansberry as well. I'm not sure, Cindy, if you happen to know her as well.
Boss.
But
I know her.
Yeah, so please join us November 10th as well, because we'll have another exciting speaker on our Vacation in Space series. And so once again, thank you everybody for attending. And Dr. Evans, thank you so much.
Oh yeah, thank you all. You all have a good evening. And log in tonight to see what happened with the spaceship that just landed on an asteroid. It's really exciting. So, okay, take care, babe.
Thank you.